it's the real thing. We go down the staircase by the loos here or back to the other end and we assemble in the car park over the road. Okay, it says welcome the speaker, that's me. I'll introduce myself in a bit. Any apologies for absence?
Bill Langsford.
Right, Bill Langsford, okay, thank you. The attendance sheet is going around the room at the moment. It can make sure you sign in. Also, the minutes of the last, or the notes of the last meeting came out with the newsletter. If there's any issues with that as a record of the meeting, I'll take that at the end. So we're pleased to say we've got 4 new members. Jacobus Zagorakis of Amy's, Fahim Wignall of Network Rail, Rhys Mason of Network Rail, and Louis Alcock from Atkin Realis. Okay, anything else, Mr. Secretary?
Nothing else to add, I don't think.
Okay, right. So we'll get down to the main business of the evening then. So what's this to talk about? So I was asked to do, well, the one thing I should say, Craig Fisher, who should have been here tonight, sends his apologies, and he is going now, we've exchanged basically, he'll be doing the May meeting on operations performance. Okay, I think that's confirmed now, isn't it?
Yes.
Okay. Right. So RCM in a nutshell. So reliability centered maintenance, not remote condition monitoring, just to confuse the issue. But right. I put this cartoon in because I think this does tend to sum up things. So you know, something's going wrong, so we'll phone maintenance because some things must be wrong. I mean, is that a maintenance failure? No, it's not. It's an operations failure, isn't it? Yeah. So I think it evened up the rowers a little bit. The boat probably wouldn't go round in circles anymore. But there is a tendency, I think, to think that maintenance can fix all things. And we're going to talk about what reliability centered maintenance is and why it is a very powerful tool. So we're going to talk about what is RCM and risk-based maintenance, as Network Rail call it. I put a little bit of history about RCM just so you can see where it's come from. We're going to talk about equipment failure and the key RCM questions. We're going to talk about functions and performance standards because it's functions that we're looking at in the context of this. It's the functions of a piece of equipment because RCM is not railway special. It's an agnostic system. So it's the functions of that system we want to look at. The functional failures and the failure modes. So what happens? We'll have a little look at P to F curves and some RCM tasks. So this is quite a high level look at it, but I think it'll give you a flavour for how it works and why the railways adopted it. So we've got two things. So reliability centred maintenance. This is an extract from a Network Rail standard, an established process which defines what maintenance is needed in order to allow an asset or system to meet the business need within a specified operating context. An operating context is really important, as we'll see later on. So that's the process RCM. Network Rail call their version of it risk-based maintenance. Yeah. So reading the description describes a qualitative, financially based analytical technique that establishes the relative worth of various maintenance tasks and serves as a continuous improvement tool. And we had a very good talk on continuous improvement a while ago, didn't we? And it eliminates low value tasks and introducing tasks that address high commercial risk areas. Risk-based maintenance evaluates the current commercial risk and analyses the costs and benefits of steps to take the risk. And I think that's really important. So we're not just talking safety here, we're talking about performance risk, we're talking about reputational risk and things like that. So, and this is an extract from a report from Nolan and Heap, which is one of the big reports. So the traditional concept or traditional approach to scheduled maintenance was based on the concept that every piece of equipment has a right age at which a complete overhaul is necessary to ensure safety and operational reliability. But what's actually happened is when we started the airline industries, were the first people to really get into this in the 1950s, and what they found is by analysing a lot of data, because by the 50s there was quite a lot of aircraft flying about, they had quite a lot of data which actually demonstrated that that is not actually correct. There is no right age for an overhaul. It's more supple than that.
Andy, they're asking online, you can reshare. I don't know why there's a problem because it's fine on. If you could reshare the slides,
Yeah, can do.
sorry,
That's right.
very good, because some people can see them with you and others can't.
Right. Let's go in again. Right.
Sorry, so.
So I'm getting big teams. So, there we go. Right. I am sharing still.
I know, I don't
Oh,
understand why Alex says it's fine with him, but other people, just, for some reason, it's not working for them, so.
Okay.
Just try
Right. Right, is everyone all right now? Okay.
Yeah.
So, right. So, moving on. So what the aircraft industry started to find was actually just doing lots of overhauls didn't solve the problem of aeroplanes falling out of the sky. And they started to have a look in a bit more detail about what they were doing and started to focus in on what the tasks were meant to do, because it became apparent just taking something to pieces and putting it back together again doesn't really make any difference. And it, in fact, it can quite frequently make things worse. And this eventually led to what we now call RCM. The name was born out of a report, Nolan and Heap in 1978, but it came from the US Department of Defense commissioned United Airlines, who were one of the big airlines in the States, to actually prepare a report on what they were doing in maintenance, because they'd started to see benefits coming out of it. And I think there's two key learning points which are really worth highlighting from that. So the first one was scheduled overhaul has little effect on the overall reliability of a complex item unless it has a dominant failure mode. So there was only a certain cases where you can have scheduled overhaul becoming effective. And the other big one that came out of it for me was that there were many items for which there is no effective form of scheduled maintenance. So there isn't anything you can do to it which really changes its life. Yeah. And I think that's quite fundamental to where we're going with RCM. So that's really a bit of background about what RCM is about. And then we'll look at how the process works. So, right. So in RCM speak, it's split into three sort of eras. So pre-World War II. So labour was relatively cheap. I mean, we're talking about going right back in time now. Mechanisation was relatively low. A lot of people were employed in factories, on working on the railway and all these other things. Mechanisation was low. The designs of machinery were quite simple, steam locomotives in the railway context, yeah. And they tend to be quite over-designed, which meant that there was a bit of redundancy in the system, so they didn't fail very often. And they were quite easy to repair as well, so there wasn't a minimum downtime. So regular maintenance wasn't a particularly driver of things at the time, and a lot of businesses worked on the basis of when it breaks, fix it. Yeah, so there wasn't really. World War II and the aftermath really started to change things. So So we started having a real shortage of manpower because then manpower was tied up in other stuff. And the demand for goods started to really grow. So we started to increasingly mechanise factories and systems and processes. And there started to be a need to actually people started looking at performing maintenance to prevent failure, because we would, rather than actually doing fixed interval maintenance, and the increase in running costs of various things resulted in a need to, people started looking at things to do with the running, like availability, like downtime in factories and things like that, actually got people starting to think about that. And that was also driven by the fact there was a huge amount of capital tied up in fixed assets. Yeah. And as the cost of that capital went up, people again became more and more interested in ways to actually seek to maximise the asset life. And then again, from the 60s, things changed again, because we'd started developing these processes in the wake of World War I through the 50s and into the 60s. So since the mid 70s, there's been a real change in industry, and particularly process industry and things like that. Downtime has always affected productive capability of physical access by reducing output, but the combination of increased operating costs and interfering with customer service again started to make it more important to industry to have reliable, predictable outcomes. So reliability and availability are now concepts which are really, really important to industry at large. So this is quite an interesting chart as well, and it shows what happened. So so this chart shows accidents per million takeoffs, versus year across the bottom. It excludes sabotage and military action, but I think it's quite interesting when you think about where we were in the early 60s, over 60 accidents per million takeoff. Well, if you carried that forward now, it's about 1.5 million aircraft in the air at any one time. So I think having accident rates at that level would be fairly intolerable, wouldn't it? But you can see the effect and where it really kicked in. We talked about in the 70s, it really kicked in, and we were doing a lot of analysis through the early 60s and that. So, so much of the improved reliability, of course, is due to lots of other things besides reliability-centered maintenance, like better quality materials, systems with greater redundancy built into them and things like that. But most of the improvements were driven in turn by the realization that maintenance on its own could not extract the required level of performance from the asset. So let's go on to think about. So back to looking at pre-World War II things. So as the industry was not highly mechanised and labour was cheap, it was a case of fix it when it broke with little regard to downtime. And this is the model that sort of people was sort of using. So the thing will happily run along for them, and then towards the end of its life, you'll get a period of unreliability, and this is when you need to do something to restore its condition. Okay, so but the studies actually started leading into other things as well. So another popular thing, you probably many of you recognise this as the so-called bathtub curve. So this is post-World War II. So failure rates again were believed to follow a pattern known as the bathtub curve. So lots of early life failures when the thing's first installed, then it settles down to some fairly steady state, and then you get a lot more failures towards the end of the life of the thing. But in fact, the research found that there are 6 failure patterns. And we'll look at each of those in turn now, in the slides. So the first one is the bathtub curve. Yeah. So it starts with a high infant mortality, decreases to a fairly constant rate, and it follows an increase towards the end of its life. But actually, only about 4% of systems actually follow that kind of thing, and it tends to be more complex systems as well. So this is the next one they found, which is a constant failure rate until the wear out zone is reached. So this is the one that was favoured before World War II, as you like, that it's going to be reliable to a certain point, then you need to intervene and do something. In fact, 2% of things actually follow that kind of a failure model. Model C was a slow increase in failures. So it gets slowly worse over time. Yeah, the increase of failures, but again, only 5% of failures actually fall into that category. Another one here, again, another model that came out. So you have a low failure rate when it's new, yeah, but then it rapidly increases and you have a constant failure rate throughout its life. But again, this is only about 7% of systems actually follow that kind of thing. So there was quite specific. Constant failure rate. So failure rate fails at any age. So it's not an age thing, it's just a random failure. And as you see, we're getting into bigger numbers now. So 14% of those things. So there's no life. There's no particular point to intervene. They just fail randomly. And finally, the one that number 6, F, yeah. So it begins with a high failure rate. So this is the sort of bedding down and things like this when things are all new and getting work. It settles down to a fairly constant level, but there is no wear out zone again. It's just pretty much constant from there. And 68% of cases actually follow that kind of a model. So there isn't any clear point at which you want to intervene. Yeah, there's not a wear out zone or anything like that. Okay. So that's really the sort of basis of starting to think about, well, what do we need to do then to improve reliability and performance? So in RCM, there are 7 questions you have to ask yourself. Yeah. So you could actually use the RCM process in the construction of something new. The Boeing 747 actually had RCM principles used in its design and construction. That's been proved to be one of the most safe aircraft that ever, really. Possibly slightly better than some of the newer Boeing creations. But the questions you've got to ask yourself first: what do we want it to do? And are there any rates or tolerances around that? So can we fix what it is we want to do? And if we can particularly give it some, be numerate about it, you know, not just we want it to work all the time. You know, we want it to work 99% of the time or whatever. How does it fail to do what we want it to do? So having identified what the function is, how do we lose that function? What causes it to fail that way? So what are the root causes behind the loss of functionality? What happens when it fails in that way? Because clearly the consequence is going to have an influence on what we want to do about it, isn't it? When it fails in that way, does it matter? So what can we do to prevent or predict this type of failure? So what tasks, and you'll see about the tasks and things that we can do in it. And what can we do if you can't find a task to prevent this failure? So they're the 7 questions which form the underpinning. They all look quite easy, but answering them isn't necessarily particularly easy. So let's think about what the things. So let's first start with function and operating context. So this is, we need to determine what the users want to do within the boundaries of the asset is expected to operate. Yeah. And we then need to ensure it can do what this users want to do to start with. Okay. So that's really important. So again, it's functions, not, and then we'll have primary and secondary functions. So why is the asset required in the first place? So for an example, office chair. So a primary function of office chair is to support up to 200 kilogram of occupant in a seated position. Okay, so that's a simple primary function. But most things have many functions and they'll have secondary functions as well. Okay, so every asset is expected to have more functions. So for our office chair, another function might be provide a means of adjusting the height. There's probably a requirement for it to be safe, isn't there? I mean, one leg and a disc is a stool, you can sit on it, but is it safe? Yeah. Things like that. So we end up with a lot of functions, and a lot of the analysis goes into thinking about what the functions are and what the functions and how the functions can fail. Okay, all follow it so far. It's all gone very quiet in there. So I think there's one thing that's really, really important as well. And again, I think as the railway industry, we're quite guilty of this. So if you think about the cases of what we could do, so if the first one is what maintenance can achieve. So the inherent built-in capability of the asset, yeah, what the asset can do, is as far as maintenance can take it, isn't it? You cannot maintain something better than it was designed to be in the first place. Yeah. Okay. So if we get into like the second one, where what it can do and we want to do is less than that, so this is what we want it to do, but that's what it can do, then maintenance will comfortably be able to deliver the desired performance, won't they? And there's a bit of margin in there. But frequently we end up in the third situation, don't we? So what we want it to do is up here. What it actually can do is here. And that's as far as maintenance can take it. And we need to be very conscious of that so when you start applying RCM in the real world, you do need to be conscious of what it was. You know, is this asset actually going to do what you want it to do anyway? Yeah. So take an example of a bridge, you want to run 25 axle weight traffic over it. It was designed for 18-ton axle load. Then probably just upping the tonnage going across it that's too simplistic, isn't it? We need to think about, because you sacrifice things, don't you? You either sacrifice life in terms of fatigue damage, or we have to have enhanced maintenance or whatever. Okay. So quite important to remember that again, maintenance can only achieve what the thing was designed and intended to do. And that's really, really important. But so secondary functions cover a wide range of things and are often described by the mnemonic escapes. Okay, and their relative importance will be dependent on the primary function and the operating context, and we'll look more at operating context. So E is environmental integrity, S is safety, C control, containment, comfort, appearance might be important with some things, protection, economy, efficiency, and S is superfluous functions. So these are things which they aren't directly related to what the primary function is, but they are things which are still important to the user. Okay. So what does that look like in terms of railway? So if we think about the functions of track, so we spent a lot of time analysing track, and we ended up with 18 functions. Yeah, and we got the top 6. Well, we've got 6 here. So obviously this is a pretty primary function, isn't it? To support and guide trains with the published axle load, line speed, and a million gross tons per annum. So again, making it numerate. Yeah. So we want to carry support and guide trains, but we also want to do it without restrictions for weight, without restrictions for track geometry and things like that. Must continue to operate in all local weather or seasonal variations. Must be a safe environment for anyone on or about the railway. Must provide acceptable level of comfort to passengers. So we're getting into secondary functions now. Must not pollute the surrounding environment. Yeah. And then there's clear secondary functions like provide a traction current return for the overhead line and third rail systems. So there's 18 functions in all. Some of them are just to do with mounting equipment on the track, but I think that gives you a flavour for what we're doing. So these are the functions that we don't want to lose. And these are the functions we then start looking at about how we can lose them. So we have functional failures and we have failure modes. Okay. So when an asset is unable to fulfill the function at the specified rate or within the set tolerances acceptable to the users, then it's said to be functionally failed. So if in types of our chair, we may be unable to adjust the height of the chair. That would be a functional failure, wouldn't it? Yeah, in the context of that. And the failure modes then start to describe events that are reasonably likely to cause the failed state. And I think you do need to be careful in here to avoid meteorite strikes and things when you're doing the analysis, because they do happen, but you've got to be realistic about what's likely to happen. So an example of that, of the failure mode for that one would be the height adjustment hand has broken off. So you can't use it, you can't adjust it. So with the functionality we've lost is the ability to adjust the height. But the actual failure mode is we've broken the handle off, so we can't operate it anymore. Okay, so we carry out the basically failure modes and effects analysis, or FEMA analysis, and we use that as a step-by-step approach for identifying all the possible failures in a design, a manufacture, or an assembly process, or product or service. So we look at all the different ways that these things can fail. So it's quite a lengthy process. Track is actually quite simple because we don't have hidden failure modes and things like that. But that's quite a big piece of work, which is the core of it. And then we also do a FAMICA, which is the failure mode effects and criticality analysis. Okay, and that extends the FEMA by including criticality analysis, which is used to chart the probability of failure modes against the severity of their consequences, right? So hence the importance of knowing the operating context. We keep coming back to that again and again, yeah? So I'm going to do some examples on that. Okay. And as I say, I try and avoid meteorite strikes. So we now start thinking about failure effects. And again, there's a series of questions you ask as part of the analysis. So what evidence, if any, is there that a failure has occurred? Yeah. In what way, again, if any, does it pose a threat to safety or the environment? In what ways, if any, it affects the production or operations? What physical damage, if any, is caused by the failure? And what must be done to repair the failure? So we can start looking at, you think about doing your analysis, so we start looking at, well, first of all, is it evident? Yeah, is there any evidence of failure at starting? So track geometry, it might be you start to lose track geometry. Yeah, that's the start of the failure. You can recognise that. You can measure. If you can't measure the evidence, you can't really do an RCM analysis on it, can you? Because you won't have any time. So an example would be a light bulb, wouldn't it? Those of you old enough to remember filament lamps, what's one thing that tends to happen just before it goes. Gets brighter, doesn't it? Yeah. And is there enough time to do anything about it in that interval? No. So it's not a useful interval. So again, we need to think about this one is clearly, originally it was all about safety, but these days we consider the environment as well. And if we think of some of the recent really nasty accidents, Chernobyl, Bhopal, Piper Alpha and things like that all had huge environmental as well as safety consequences, didn't they? So those are the questions that we ask ourselves. And the answers then start to come out in the failure consequences. So we have hidden failures, safety and environmental consequences, operational consequences and non-operational consequences. And these are all quite straightforward, really. So first one, it has no direct impact by itself, but can lead to multiple failures, which can have serious consequences. And a really good example of that is something like a smoke detector or a standby generator. When do you find out the standby generator won't start? When you need it, don't you? So when the switch is over to the standby generator and nothing happens, you find out your smoke alarm isn't working when your house is on fire, don't you? So you can do things to check that it's functioning properly. You can test it, but you will never know until it happens for real whether it is working or not, won't you? So hidden failures are quite an important thing, and they are something that, as you build complexity into systems, you need to be wary of hidden failure, because that's failure. You're introducing new failure modes, aren't you? Okay. So, right. Safety environment. So has the safety consequences that could kill or injure somebody or pollute the environment. That's fairly straightforward. And again, if it's got these consequences, you can't just ignore it, can you? You've got to actually take action to do that. Yeah. Operational consequences. Now, in some cases, there may not be any safety consequences. If you're making widgets in a factory and the machine stops, the world can probably live without widgets. So it doesn't have any safety consequences, but it can really bugger up your operations, can't it, in your factory, or it can stop the trains or whatever. So that's the next level down. We're thinking about that, customer service and things like that. And then there are things which are evident failures that don't affect the operation and do not increase cost above the repair costs. So these are, if you like, the lowest thing. So yes, it's failed, but it doesn't really have any great consequence. Yeah. Which is clearly also going to colour what you're going to do about it and how much effort you're going to put into not them. Okay. So I say in track, we don't have many hidden failures, but obviously we tend to have things which fail wrong side as well. So, okay. But we don't have much that doesn't have operational consequences, do we? So if you think of it in a track context, you know, whether it's a broken rail or a rail defect or whatever. So having done all that analysis, we then start looking again in the context of RCN, we are start looking at what you can do about this. And we'll come to the charts in a minute, which will hopefully bring it all together a bit more. So we have three different types of tasks, and they're proactive tasks. So we have scheduled on condition tasks, we have scheduled restoration tasks, and we have scheduled discard tasks. Yeah. So for the vast majority of things, and this is certainly track, we get a warning, don't we, that before failure. Yeah. They're called potential failures. And they identify physical conditions which indicate that a failure is likely to occur or is in the process of occurring. So things like vibration monitoring is used in plants and machinery. We use track geometry. Yeah, so the first report of deteriorating track geometry is a really good warning. Your car will have a warning light which tells you the oil pressure's gone. Yeah, so again, you need to do something straight away, don't you? The warning lights and things like that. So they could be hidden failures, the indicator not working. But so there's scheduled on condition tasks. So this is about going and doing something once you get a warning. Yeah. We then have scheduled restoration tasks. So these are the things like, you know, once this has happened, we remove the component and replace it with another one. So it's either remanufactured or we take the assembly apart and do a proper overhaul and bring it back to new condition. Okay. And then the final one is a discard task. So we talked about light bulbs, didn't we? So if we do a statistical analysis of how long a light bulb lasts, yeah, you can with some certainty produce a good normal distribution, can't you? Very few of them fail quickly, and very few of them go on to enormous lengths of time. So, for instance, like something like signal lamps, it's changing now with LEDs, but with signal lamps, you could say, right, I want to catch so many percentage before they fail. You could actually fix a life in hours, couldn't you? And say that at the end of this period, I'll just take the bulb out and throw it away and put a new one in. And that way you would eliminate the numbers of failures, wouldn't you? Yeah. But you need the statistics to support that. So, but that's the thing. In track, a scheduled discard task is changing the pads. That's come out as that. It's probably not worth waiting till they've worn out, because by that time you've possibly buggered the sleepers and you've probably got well foot corrosion problems. You're probably better off, based on your site conditions, saying that after 20 years, 30 years, 50 years or whatever, we'll just throw them away and put new ones in. Yeah, don't wait for it to fail. Okay. So what are the actions that come out? So when we go through the chart, it'll all become clear. But so what are the default actions that come out of it? So it's failure finding, which is checking the hidden functions to find out if they have already failed. Yeah. That's always a difficult one. So we get in things like standby pumps, standby generators, and all that kind of stuff. We do on condition tasks. And this is probably the most common one in track, is we go out there and we actively look at a particular period of time to see if something is failing. And we establish those using the P to F curve. We can establish how often you need to look to make sure you will always pick up the early signs of failure. Redesign is quite important. So if you're coming down and you find you can't do failure findings or on condition, you're really going back into redesign. Now, redesign is not necessarily, it might be about redesigning hardware, but quite frequently it's about changing the procedures, retraining people and things like that to actually change the way we do things. So redesign is, and you can come down to compulsory redesign, is about when these things are not practical. Yeah, basically. So redesign does come into it. And then the final one is no scheduled maintenance. So nothing can be done to prevent or predict this failure, and we just let it run on. Bulbs are a good example, aren't we? At home, none of us put in preventative maintenance for light bulbs. You might have a light bulb spare in the cupboard that you can replace it with, but we don't attempt to stop the light bulb failing, do you? Okay. So, and statistical analysis, I mentioned right at the beginning, in the 50s, the aircraft industry started compiling all sorts of statistics and looking at different things to try and actually work that out. So this is coming back to our number of failures time curve that we looked at before. So the mean time between failures is the average time the asset lasts before it fails. Then we're talking about changing light bulbs and things like that. So if we replace it at a time scale, a time scale before mean time, then we'll actually eliminate some of the, okay. So this is it, basically. So the asset, if you do give it a life, yeah, its identical asset operates reliably for a period of time before they reach the wear out zone when they're likely to fail, and performing preventative maintenance at or just before that will lower the numbers of failures. Yeah. But determining this life is quite difficult because obviously there's a lot of statistical randomness in it. So again, it depends on the consequences of failure. If this means the light goes out at that point, if you've missed it, then if it means the airplane falls out of the sky, it's a rather different set of consequences. And so statistical analysis is really important. But how do we actually do that for something like track? So what we use is a P to F curve. And I think some of you have been bored by P to F curves from me before. So this is the P to F curve. So this is the function of the asset. So this asset here is functioning really well. Yeah. Point P is the point at which, to use RCM speak, the operator can see that it's starting to fail. Okay. And F is the point at which we've lost the functionality that we want. Okay. Now that time can be hugely different, can't it? Again, depending on the operating context and depending on the equipment. So a light bulb goes bright, fail is fractions of a second, isn't it? But for a piece of track, the point, if you don't do anything, yeah, the point between where it first starts to show geometry faults, yeah, and the point at which it's no longer fit for traffic, so we put a speed on it, which is one of our functions, isn't it? That could be years, couldn't it? And it will be different in terms of the operating. If this is along the West Coast Main Line or the Great Western Main Line, that's going to be a lot shorter than it would be up Central Wales Line, wouldn't it? Where this could possibly be decades, wouldn't it? Yeah. So the operating context is really, really important. And as I said, you can only do a task if we have a point P. If there isn't a point P, you can't apply this kind of approach to it because there's no warning, is there? So it's really important. So for a given operating context, so we use track category, which is line speed and tonnage, don't we? We can work out what, if no action were taken, how long it would take to get from point P to point F. So it's a track example. So our function is to support and guide trains with the published axle load, line speed and tonnage. So the first thing we'll get probably is an alert limit geometry fault. Yeah, so there's nothing to worry about. There's no mandated action for that. But as soon as you've got that, you can start planning it, can't you? You can start planning to do the work. If you just leave it, eventually we'll have an intervention limit track fault will occur, which we're now into the position, or we'll get a rough ride report. So we get into a short scale where we've got to do something about it now. They might end up with a speed restriction on it and potentially even a derailment at the end. But that's gone way past our point of failure, isn't it? The point of failure is when the train's no longer being supported and guided at line speed. Okay. So, and here's an example for a rail defect again. So same function, but this is another way that function can fail, isn't it? Broken rails, yeah. So point P would be a detectable visual. So start of a squat, no depth yet, but you can actually see it on the surface of the rail. An ultrasonic defect picked up during testing, or an eddy current defect in the rail. Again, just leaving it, this is potentially quite a long time. But eventually, if you left it, you will end up with a rail defect, which requires immediate action, wouldn't you? So we're putting a speed on it. We've got a short period of time to take it out. We may have to block the line or impose a speed restriction. And again, potentially, it could break the rail, couldn't it? So which could lead to a derailment. Right. So that's P to F curves. Yeah. And we'll talk about the implications of that in. So what are the implications? So if we can check for a point P, we can tell if the equipment is beginning to fail. Yep. Which allows us then to do some particular task on it. If the P to F interval is long enough, yeah, that it's practical to check for point P, yeah, and have time to correct the failure before the equipment reaches F. But in practice, if we can check for point P at a frequency of half the P to F interval, then we should prevent the vast majority of failures from actually occurring. Yeah. Yeah. And checking for point P is called an on-condition task. Yeah. So it's performed based on the usage, yeah, in terms of where this asset is located at half P to F interval. Yeah. That will be sure. So go back to that again. So if you ultrasonically test at half that interval, you'll be sure of always finding them, won't you? Yeah. Good. It's all making sense. Okay, so P to F interval is the time between the occurrence of the potential failure and the failure occurring, and you can see it there on that chart. Okay. So what are the benefits of, I mean, I think one of the huge benefits of RBM is it is a very proactive approach. Yeah. So if you find this fault, and you deal with it up here, what's the risk of a broken runner? What's the risk of a rough ride report? And that they're all very small, aren't they? And I think there's a bit of a tendency in the railway at the moment, because we've got a culture of compliance to standards, and we tend to operate down here. So we find the thing, we sort of fix it, but we don't restore it like necessarily like back up to here. We tend to be working in this area, things like geometry and that. We don't do enough sort of proactive work. So I think the challenge is actually working out how you get from here to here. But where we have done reliability centred maintenance, it has actually been very successful, provided you do it properly. Yeah, because it really encourages you to get things fixed quickly. Yeah, as opposed to waiting till you have to do something. So whatever you want to say, anything on that? No. Unfortunately, some of the senior management don't get it yet, but there we go. So earlier intervention allows more time to fix the defect, and the defect will be smaller as the rectification will not be driven by MAC codes. So this is how you save money out of it. So what you're fixing here is a little defect, isn't it? Something that's simply fixed, doesn't cost a lot of time and money. You can plan it when you want because you've got loads of time. It's not even years. So you can give yourself a generous time to plan the work, to plan the access, to scope the job properly. And that allows better utilisation of the access, better use of resources, lower costs of intervention. So eventually you start saving money, even if you have a similar number of defects because you're dealing with them in a different way. And just because the inspection point will identify point P early, and thus allows plenty of time for rectification, you do need to plan the work straight away. So if this is 3 years and 22 days, you don't want to start planning the job at 3 years and 20 days, do you? You want to start planning it immediately, because that's the way we actually deal with it. Yes.
Can I come in? Just to say, yes, it's wonderful to get near the B point, and the F point is years away.
Yeah.
But isn't there a bathtub curve on cost in getting back to P? And that might be why senior management is not too keen on it yet.
But if you're going to do operating down here, so my counter argument is this is compliance culture that drives this behaviour. Yeah, so you do something with it when you have to, but often you can't restore it because it's got in quite poor condition. But our lords and masters tell us that we want a high performing railway.
But they also say, the even higher masters say you ain't got any money to do it
Well, but it costs you less to do it, yeah.
in the long run.
Yeah. As I said, that's the clever bit, is thinking about how we do that. We have done it in Wales. We've done it with rail defects very successfully in Wales. We've been at it for about 10 years now, and we are by far and away the best in the country for managing rail defects. And that was done through three things. It was reporting all visual rail defects, so they get in the system early. Yeah, it is a proactive approach to getting them tested and things like that. And it's a proactive approach to getting them out. So every defect is actioned and removed. Yeah.
And retesting defects fits this curve perfectly, doesn't it?
Well, look, yeah. So retesting a defect is a classic. So we find it here,
Instead of
and we retest it, and we retest it, and we retest it, and we retest it, and we retest it. Oh shit, we've got to do something with it now. So there is a real benefit doing it, particularly if you want a high performing railway. Because this is the point. It's about performance, about stopping losing that functionality. And I don't think you can take an RBM approach even if you haven't got an enormous budget. Because if you don't take that long-term approach, I was talking to one of our graduate engineers there, and he was telling me how it had been explained to him. He worked in the bridge office. He was doing bridge exams. We're better off inspecting defects in bridges than we are fixing them, because the minor works budget won't fix it. So, yeah, in the short term, but that's completely unsustainable long term, isn't it? Because the defects just get worse and worse and worse, and we get to the point where, we can't repair it anymore. So.
Or you end up in rolling stock field, you end up with a Talladega accident.
Yeah.
Because the standards were locked.
Yeah.
And they hadn't been properly maintained.
Yeah.
Definitely.
So it is, I mean, I hear absolutely what you're saying. That's the argument you two do tend to get back. And I think there's a tendency to think this is going to make a difference overnight. It isn't. It is a long-term view, but it is a long-term view moving towards a more a sustainable future, and more to the point, a high-performing future as well.
And preventing a serious failure occurring.
Yeah, and you'll never entirely prevent serious failures, really, because things conspire against us. But if you think about what we did before we had all ultrasonics and all the rest of it, then track was kept in a pretty high standard, wasn't it? Because it became evident. So if you haven't got ultrasonics to look for rail defects, you want to keep it good, don't you? So you put things right as soon as they start to go wrong. So there's nothing really new conceptually with it, but certainly not in the railway.
Andy,
Yes.
so in terms of finances, it does quite quickly work out to be a lot cheaper. For the defect example, each of those retests requires a team to go out, costs X amount of money, and then the emergency response at the end, disruptive access, and a larger defect, like you said, it quite quickly becomes a cheaper way of maintaining this. Whether it's track faults, doing a quick.
053 was another good one that's facing switch exams. Waterloo section, we're having real problems with switch wear and the implications of performance hit. So they introduced quite a proactive approach to doing the inspection. So they go there mob-handed as well. So they can do grinding, they can do checking on how the last lot are working. So does it stop the switches wearing out? No, it doesn't stop the switches wearing out. Does it stop the embarrassing phone call at 5 o'clock on a Tuesday morning saying I just blocked the suburban side of Waterloo? Yes, it certainly does. Yeah. So it's had a huge impact on performance because they're just doing it. They're operating up here. They're fixing stuff they find when they find it. So it can be done, and it doesn't necessarily need a huge lot more resource or money into it.
But it does take it takes a different attitude to move from the bottom end of the curve back up to the top of the curve.
Absolutely.
And it's either cash, well, it's resources, be that cash, manpower, materials, possession time in railway context, and the ability to actually do it.
But this, but
You're going to get the planning there and say, no, it's not a next week job, it's a this week job.
well, it is a change of attitude, and that's one of the reasons I did this paper originally, to talk to some people who are doing RCM or having problems with some of this, because it isn't a complete approach. Once you've decided you're going to go down this route, you can leave yourself longer, you eliminate lower inspections, but you've got to do the actions which you've agreed in your analysis are the way to manage this, which is to intervene and do something within a certain time scale and things like that. Okay? Right. So on condition task is checking to find the point P, the potential failure, and it's beginning to fail. And failure finding is checking to find a hidden failure. So particularly, so these are failures which are not evident to the users. And it's done by performing a failure finding task. And we can see that the device is still capable or not of performing its function. Yeah, and I say it's mainly to do with protective devices. So this is the decision diagram. Remember, going right back to the beginning. So hidden consequences. So the failure is not evident. Yeah. Safety and environmental consequences. Yeah. Operational consequences, takes you down this leg, and then non-operational consequences takes you down this leg. And we'll look at the top of the chart and just have a think about some examples. Okay. So for each of the failure modes, let's go back. So for each of the failure modes being established for a different type of equipment, we use the decision diagram, which is this thing, to work out what, if any, maintenance task we could or should perform. And for each failure mode, after working through the decision diagram, we have an outcome, which will be one of the following. So it's a scheduled on condition task, a scheduled discard or restoration task, a scheduled failure finding task, a redesign or no scheduled maintenance. Yeah, simple yes, no tree. And we'll have a look at an example now. So this is the top part of the tree. Okay, so that's just going through my notes. So this is the top part of the tree. So let's have a think about an example here. So, so we've got two identical generators. Okay. So one is being used to provide power at a music festival, and the other one is being used as a standby generator at a railway signalling centre. What's happened to that? That's it. That's the wrong button. Okay, so let's think about the music festival first. So, will the loss of function caused by this failure on its own become evident to the operating crew under normal circumstances?
Yes.
Yes, because the lights will go out, won't they? So we come down into here. Does the failure mode cause loss of functionality or secondary damage which could have a direct adverse effect on safety or the environment? It's debatable. The lights are going to go out, aren't they? Yeah. So if you say no, yeah. So does the failure mode cause loss of function or secondary damage which could have a direct adverse effect on the operational capability? Yeah. Well, yes, it will when the power's gone off, so the music's gone off and everything else. So it comes down and it's an operational evident failure. Okay. So that's simply saying it. If we go back to the other chart, we've got an operational evident failure. So we then go on, is it on condition task worth doing and feasible? So there would be some on condition tasks. We could check if it's full of fuel, couldn't we? We can make sure that the thing is properly serviced, etc., and you can work down things out. Right, let's now think about our so same generator, exactly the same generator, but this is used as a standby generator or at a railway signalling centre. So will the loss of function caused by this failure mode on its own become evident to the operator? No, because it'll only become evident when the power goes off and it doesn't start. So we're going down this route now. So no. Does the failure mode in combination with the further failure cause a loss of function or secondary damage, which could have a direct adverse safety implication? Yeah. So it could do. So that's yes. Going down this route. So it's a safety and environment one, but it's a hidden failure. Okay. So as you can see, you can work through in different circumstances. Another example we could do is a pump as well. So we'll do that quickly as well. So we've got two pumps, identical water pumps. Okay. So one is circulating water for a decorative fountain in a city square, and the other one is circulating coolant through a nuclear reactor. So identical pump, same outputs and everything. So look, think about the fountain at the moment. So will the loss of function caused by this failure immediately become evident to the operating group? Yeah, because even if somebody rings up and said the fountain's not working, yeah, it becomes evident, doesn't it? So it comes down this side. Does the failure mode cause a loss of function or secondary damage, which could have an environmental or safety impact? No, it doesn't. So we come down to here. Does the failure cause a loss of function or secondary damage, which could have a direct adverse effect on the operational capability of the asset? So probably not. So we go down into non-operational evident. Yeah. Yes. Okay. You might say, well, it's let damage our reputation, so you might end up in here. Yeah, but okay. So now let's think about the nuclear, but the pump in the nuclear reactor. So we're up here again. So does its failure become evident? Yes. Yeah. So coming down here. So will it lead to safety and environmental consequences? Yeah. Yes, it certainly will, won't it? Yeah. Okay, so we come down this one to the safety and environment. And again, if you go back to the other chart, you can see how the different tasks work. So the operational one, non-consequential operation one. So again, is there something you can do to stop it happening? Yeah. If yes, you can do. If no, then we just go to scheduled restoration task. So you could say, well, could we just replace the pump after so many years or whatever? But again, yes or no, just yeah. Notice in here it says it also says, is it technically feasible and worth doing? Yeah, because the fact that it's technically feasible might not mean it's worth doing. That's a business decision, isn't it? Yes. Yeah. We have a brilliant technical solution for cracked rail ends called cold expansion. And we cold expand all new hulls. Is it worth going back and cold expanding the holes in our existing jointed track? It would be nice and it would solve the rail end failure problem, but it would be so expensive. Unless the rail's going to remain there forever, it's not worth doing. So as you see, you can come down to here, things like scheduled discard and things like that. Okay. So how are we doing for time? Right. So that's the full chart as in the book at the moment. So as you can see, we've got the 4 legs. So hidden, safety, and environment. Environment wasn't really in it originally, but that came in later. I think as people became more aware of the implications of that thing, and then we've got the operation side here. Now you notice that some of these they come down. So if you're coming down here and you can't do the yes, yeah, you then have to start thinking about compulsory redesign. Yeah. So that means looking at the process and systems and things like that. So what it effectively telling you is you've got something which can cause serious problems as a hidden failure. And we haven't got an effective means. So we've got to think of another way of managing the problem. Same with the, it does bring you down. It rarely brings you down to that one. But we've done certainly in Network Rail, we've had several redesigns. Because we highlighted some failure modes we didn't realise we had. Chair screws, actually our controls on broken chair screws were really, really weak when we did the analysis. And there's nothing in 001, the existing maintenance standard, much about it at all. It tells you to do something when you find them broken. But you then get into the question, well, how often do you have to go and look? You know, how many can you tolerate before you? So, and we're introducing some checks on that based on condition and various things into the new standard. So, right. Yep. Right. I hope that made some sense. Any questions? Any questions online?
Yes, Andy.
Yep. Alex.
Yes. Number one, thank you. Fantastic present as always. Just a thought on modern sensors and AI. And its impact on RCN. So, and obviously my concern is the danger of garbage in, garbage out, and that need to have a human intelligence and overview. And how do you think that would be if you redid the analysis, for instance, done in the 50s and 70s into given modern AI, etc.?
Well, it would certainly have an effect in terms that, I mean, I think AI again could be a help because it can crunch through a load of data very, very quickly, couldn't it? Looking for patterns and things like that. So I think that could certainly help. And the work we're doing with Insight, which is our new engineering support tool, has already started doing that because as well as track geometry and all those things, it now has in whether the earthwork's in good conditions, whether it's in a cutting or an embankment and all sorts of stuff like that. And that's already starting to throw up some interest. So I think AI could help. But again, the big risk with it is actually producing sort of false. If it can't report the BBC News accurately, we don't want it reporting other things. But I think more to the point for me is just buying the whole concept that once you found this thing, you just deal with it. Yeah, deal with it while it's small and easy to deal with. It doesn't take a load of time, doesn't take a load of people and things like that. Because once it's dealt with, it's gone, isn't it? It's disappeared from the system and is no longer a threat. So I'm not sure whether that answers your question or not.
Oh, it's a sort of. I had if anybody else hasn't got another question, I had a secondary question about and it was about rail defects. So you can fully understand. I've brought the knowledge about managed rail defects here to Brisbane, and it works well. But that early differentiate between kittens, as in not all kittens turn out to be tigers, some turn out being cats, and they're the ones you don't worry about, but the tigers you do. But I think maybe that's where AI can help a little bit, as in differentiate between things you worry about, and ultrasonics is that, and things you worry less about.
So, I mean, one of the things that AI is allowing us to do with the AVA system, for instance, is find visual railway defects. Now, it's becoming, Dave Clements is doing a lot of work on that, and it's already proving its worth in terms it'll find blemishes on the railhead for you. So you can have a look at them and decide, well, perhaps we need to ultrasonically test this and get it into the system. So it's already helping in that respect as well, yeah. Because again, it's this. It's, yeah, it's found a broken rail, which the UTU failed to find. So there is huge potential there, but I think we just need to use it carefully, don't we? So.
Thanks.
It's worth saying as well about the one challenge we've had is about the tolerance of you're so reliant on the track geometry recording data.
Yeah.
And that P point, isn't it, being consistent.
Yeah.
So as, because Alex was talking about, garbage into the system, garbage out.
Yeah, but we've never been back, and when we first established PLPR, for example, which uses this 10mm.
Yeah.
Yeah. So, I mean, has anyone been back and challenged? I mean, that's me and a couple of other people sat in a room in York, came up with the chances of having a defective IRJ without a dip angle are extremely small, aren't they? As you'd expect it to deteriorate, and if the plates are cracked, it'll flex more. But nobody's been back yet and readdressed that. So perhaps it is time to readdress that again. Yeah.
Mm.
But it's the usual challenge. If you set the threshold too small,
Yeah.
so you set the threshold to be sure of catching everything, and you tend to end up with a lot of false positives. Yeah. And that's the problem with these kind of systems. You don't want to send people chasing off after stuff. Because again, you've defeated the object of getting people off the track and that kind of thing, haven't you? If you keep sending people, and that's one of the problems with UTU at the moment, isn't it? We have to send people there to verify the defect that's been found, because the train gets one shot at 30 mile an hour or faster if they're going on. Whereas a team of ultrasonic testers will stay there until they've definitely establish what the defect is and how big it is and things like that. But yeah, I mean, there's the challenges with all this sort of thing, isn't it? Yeah, I think the biggest challenge with using AI is I've yet to see AI use a shovel. So and I don't think the challenge is not inspection. We're pushing ahead with inspections and getting better and better and better at it. But we're not getting in the same place with the good old task of going out there and do some measured shovel packing or weld up a rail defect or whatever. So yeah, interesting stuff. But right, any more questions?
Robert Wilkins has asked one online. He's asked, has NetherRail looked at updating RCN2 to the more new RCN3 process?
Yes, is the answer to that. I've not been involved in that process. I don't think it would make a huge amount of difference to what we're doing, but certainly the intent is to carry on, updating that program. There's a working group, you're on the working group, which will be looking at things like that, whether it's worth doing that or not. So, okay, but yes, we're aware of that. Yeah. And another thing that has a huge effect, and this is where AI does come in, is remote condition monitoring now, isn't it? Of one sort and another starts to make a big difference to the, what you can see on site without necessarily going there. So, but there's lots of things to look at like that. So, but I think the biggest benefit comes from just combining data. A rail pit breaks from corrosion pits on the bottom of rails needs input from the geometry side, doesn't it? Because it's the dynamic forces from the geometry which break the rails, not the rails will go rusty. If you take them outside and leave them lying around for 50 years, they will go rusty. We're never going to stop the corrosion pits, but we can actually react better in places where we've got bad geometry. Yeah, poor geometry, big changes of stiffness and that kind of thing. Yeah. Any other questions? Right, well, thank you very much for your time. I'll revert into chairman mode now. So, I don't know who's going to do a vote of thanks. Okay, right, we'll do that. Yeah, so, okay, we'll do the vote of thanks then. I called one hand to propose a vote of thanks. Yeah, absolutely. Yeah.
Thanks very much for that, because I didn't really know too much about it. But I know there are old school thoughts. If it
Thank you.
ain't
Bye bye.
broke,
Cheers.
don't fix it.
Yeah.
And then there's the other one, then it's come up to a schedule and you've got to change it every time the schedule says you've got to change it. And between the two, there's an awful lot of time in some cases.
Hmm.
And in the case of our dear old light bulb, there ain't no time at all.
Yeah.
And we're here talking about the railway, which until last year was capable of carrying my mother-in-law, who since died, and that's recorded. But
I would start actually on the journey.
To say to myself, in assessing railway track,
Yeah.
would you let your mother-in-law travel over this piece of ground? And it brought forth little titters, even from Saudi Arabian railwaymen.
Yes.
When they translated it into Arabic.
Yeah.
So, thanks very much for this discourse. And I cannot still get away from the fact that getting from at the bottom end of, if it ain't broke, don't fix it, to schedule is that we can fix it next week, can cost an awful lot of money to get there. And Network Rail say, plead poverty all the time, saying whatever CP it is.
Well,
We ain't got no money.
What I will say is, in Wales, with the rail defect management thing, we set out down this road, I said over 10 years ago now, we set out, that's when I was the RAM and Dave Clements was the rail management engineer. We'd started it when I was a PWM, I already didn't. We didn't bring in any additional resource. We haven't changed really the number of defects. We're still finding a similar number of defects. But if you look at the database now, the number of defects which require urgent action or a speed restriction is absolutely tiny now. And the vast majority of our defects are now sitting in there in the 6 to 12 month bracket, yeah, or up to 3 years bracket. And we can plan those efficiently, can't we? Because you can then, you're not struggling to find access, the access which buggers the trains up. You can plan it into access in 6 weeks' time, can't you, or 3 months' time? Yeah.
Years ago, I was doing something similar, notably in the Port Talbot section, on a Friday evening, in removing defective rails, normally from the up main.
Yeah.
And this was largely to do with 3,000 tons of trouble that used to go
Yeah,
from Melbourne to Llanwern.
Yeah. Wheel burned all the way up the Stormy Bank.
Yeah, and it was a question, in those days you could do it, it was relatively cheap, it didn't affect the weekend manpower because it was a Friday night shift, and very likely all the manpower was wanted Saturday nights. So that's what we did, and it removed a lot of potential rail breaks and disrupted positions to do.
Yeah.
And Nigel Fairbrother, in the back there, was very kindly, once we proved that we could do it in about 2 hours, with 2 welds between passenger trains over hot welds. Don't tell me I can't.
No, I'm not going to say that. What I'm going to say is that's exactly the kind of thinking which supports this, isn't it? So we've identified a failure mode, yeah, a functional failure we don't want. We don't want a speed on, yeah.
Yeah.
So we've looked at all the different things which can cause us to have a speed on, through rail defects, through geometry and all the rest of it. And then we say, right, well, so we're going to probably put in an on condition task, aren't we? We're going to expect it to find the point P's, yeah, which we do. We run the track geometry recording coach, and then we sit there until somebody says, oh my God, we've got to do something about this now, or we get a rough ride report. So it is an attitude as well. Yeah, there's nothing new about this at all.
There's another interesting topic of this subject, which is now, because Port Talbot blast furnaces are closed.
No, sounds like one coming your way.
The down main line is now getting knocked to hell between Newport and Port Talbot with heavily loaded freight trains.
Yeah.
for the first time, I think, just about ever.
Yes.
And it would be interesting to know from both Network Rail sources and from Port Talbot, how, which is there in Port Talbot, taking the end user bit, how that's all changing.
Yeah.
I don't know if there's anybody here that wants to comment on that. What's the present situation? Is there a different expectation? And, and should we be looking at that as another topic in a couple of years' time?
Yeah, could well do. I mean, in its immediate effect, it's going to reduce the tonnage, which will start pushing out inspection frequencies and things like that. So again, applying the RCM type rules, we will stop doing certain things at those and start pushing the frequencies out. So you don't usually end up doing something. The tasks that disappear, they go out and have a wander around and have a look. Tasks, you go there and specifically look at something, and you set criteria to actually. So rather than is the sleeper cracked, is you how wide is the crack? Because the cracks we're worried about in sleepers are the ones where you're letting the water into the reinforcing, aren't they? Not the ones on the surface.
So are we getting an increase in defects? Are we getting an increase in pad wear?
It is coming. Rail defects are going up, and they're modelled to go up even more because we're not doing enough track renewal. It's as simple as that.
But in
We're not.
the special context of Newport Talbot, is there a change in defect discovery on the?
No, the overall numbers of defect we find are relatively stable. Yeah. So we find X number in a period or 3-month period or whatever. The difference is because we deal with them early, we still haven't got a big increase in actionable defects, as in actionable mandated action. So
Watch this space.
watch the space, yeah. But yeah, and it is, as I said, this is not a silver bullet, but it is a way of doing it. And as you can see, it is one that's demonstrated to work well, but you do need to do the whole thing. Yeah, you need, having fixed your new timescales, you need to stick to them and things like that. And we've had some problems within Network Rail with pushing the inspection frequencies out, but not reacting quickly to the work. So you've lost, there's no such thing as patrolling under an RCM regime. Nobody goes and walks the track once a week anymore. It may be once every 6 months, if for certain tasks or whatever. Yeah.
Anyway, back to
voters, thanks. Well, the second.
Would you join me, Kevin?
Right, thank you very much, and I hope you enjoyed it. So our next meeting is this sounds an equally fascinating subject. So earthworks on the core valley lines. So I think from James Dyke for Transport for Wales. So this is the valley lines, of course, are now the infrastructure is no longer, the infrastructure manager is no longer Network Rail. It's now department, the Transport for Wales. And I think they've found out what they've bought now. So this should be quite interesting. Right. So that's the next meeting. That's on the 14th of April in this room. And if there's any comments on the notes of the last meeting. Right, we'll take them as a true copy of the meeting. Right. So I'll certainly be wandering over to the Prince of Wales if anybody wishes to join us for a pint after the meeting. Otherwise, I declare the meeting closed, and I'll see you next month. Thank you very much.
Thank you.
Thanks, Andy. Brilliant.
It's now an oil tanker at the bottom of the North Sea.
Hmm?
It's now an oil tanker at the bottom of the North Sea. There was a collision this morning, wasn't
Yeah, I saw the pictures of it. It's pretty dramatic, wasn't it?
Yeah. Tanker was well ablaze. That doesn't make up on the bottom. They went down the road.
Yes.
Exactly. I'm asking the question.
Yeah, so And go to the, see how.
Right. All right.
Yeah.
Sorry. Make me look at that.
Sounds good.
Yeah.
I think we need to revisit it something, because I think I originally did this at Bristol. Because Bristol, as you know, had some problems with some of the stuff they'd done under 663. They'd been